Hi everyone. This video is the solution to example 1 on the topic of unit load method. In this example, we're going to be doing a cantilever beam with constant rigidity EI and has a UDL W on over the span L. In this case, we're not going to be using any numbers, so this is going to be a parametric problem where at the end the solution will come as a function of W, of L, and then of EI. What we're interested in finding out in this problem is the vertical deflection and the rotation at the tip of the cantilever. So in the theory behind the unit load method is to separate the real structure from the virtual structure and then do a calculation to find the displacement we're looking for. In this particular case, the real structure looks exactly like the one we're trying to calculate. So it's a cantilever with a UDL W. And the virtual, in this case, we're going to try to do first the vertical deflection. So we need a virtual structure that has a load of 1 kilonewton in the vertical direction and at the place that we want to measure it. So it's going to be the vertical deflection at the free edge. So we apply a 1 kilonewton pointing down at the free end. So when we establish this, we can then do the bending moment diagram for the real structure and then do the bending moment diagram for the virtual structure. In this case, they're both straightforward. The bending moment for the real one is a parabola with tension on the top, and then the maximum moment that we're going to get in this case, which is equal to the reaction, is going to be WL times L over 2. So WL gives you this force in the middle, and then multiplied by the distance L over 2. So therefore, we get that this maximum is WL square over 2. And this tension on the top, so we call this moment negative. In terms of the virtual case, is pretty similar. So we have tension on the top throughout, but now it's not parabolic, it's triangular. So the entire moment will be 1 times L, so we get that the moment is L. Now that we have these two diagrams, we're going to use the principle of virtual work that basically says if you want to find out the displacement delta, this is nothing more than doing the integral of the moments real times the moments virtual divided by EI. So basically we can say that our displacement delta is nothing more than our parabola times our triangle divided by EI. Now, to do a parabola times the triangle, we need to check a table that tells us how much this is going to be equal to. So I have the table here. So if we want to do parabola times triangle, we're going to do this parabola times this triangle since they're growing in the same direction. So the solution is 1 over 4 ACL. So I'm just going to write that down for now. 1 over 4 ACL. And now we need to figure out what is A, what is C, what is L. So L is nothing more than the span of both the triangle and the parabola, and C is the value of the parabola, and A is the value of the triangle. Although if you swap them, the solution will be the same. So now we write that this displacement is going to be 1 over 4 times the value in the parabola, which is WL square over 2, times the value of C, so the value in the triangle, which is L, and then again times L, that comes from the formula. So at the end, our solution will be WL to the 4 divided by 8, and since this is positive, means our displacement is going to go down. So this is it for the displacement of the tip, but also this question asks the rotation. So the rotation is going to be very similar, but now the real structure, let's do it here on the side for the rotation. So the real structure is going to be exactly the same as the one before, but now the virtual is going to be with a moment of 1 kilonewton meter at the end of the cantilever. So I'm just going to draw the other one. Now in both of these cases, we're going to do the bending moment diagram. And in the case of the real, it looks exactly as it did before. And now in the case of the virtual, the way I draw the moment here, we're going to get tension on the top. And the only thing we have to balance this out is another moment on the other side, which means this is going to be constant tension on the top with a value of 1. So now, if we're interested in finding out this rotation theta at the tip, the value of theta is going to be nothing more than the integral of these two moments. And all of this divided by EI. In other words, this value is going to be the parabola times the rectangle divided by EI. So if you look back into the table, now we're going to do the parabola times a rectangle. So this is heat. So we're going to do 1/3 ACL. So to finalize, A is going to be again WL squared over 2. C is going to be the value of the rectangle, so that's just 1. And then L is going to be L, because that's the base of both our parabola and the rectangle. So at the end, we get WL cubed divided by 6. And again, since this is positive, it means the rotation will be clockwise. So at the end of this problem, we figured out that no matter what is the load W and what is the span L, the displacement here is going to be WL to the 4 divided by 8. And this rotation, so when this loads, obviously this is going to do something that does this. So this rotation here, right, this angle, is going to be WL cubed divided by 6. Before we finish, there's something that I missed, which is the EI at the end. So obviously, depending on the rigidity of the beam, the displacement and the rotation will be different. And here, what happened was when I substituted this, I need the EI to stay here, I need the EI to stay here, which then means the EI will stay there. And also, this is true in this case. So 1/3 ACL divided by EI, this divided by EI, and at the end, we need an EI over there as well. And that's it. So now we finalize this problem. Thank you for watching and have a nice day.